Thank you everyone for attending this morning. We really appreciate you taking the time out of your day, or I said this morning, but perhaps evening or afternoon, maybe even middle of the night, depending. We are so excited to be able to have Dr. Onno Oncken with us this morning for his talk entitled Revisiting the Subduction Channel, Current Understanding and Open Questions. Before we get started this morning, I just want to say a couple of things. Translated closed captions are available. You can just turn them on using the buttons at the bottom of your screen. And then please feel free to ask your questions either using the Q&A feature or the chat. Either is great, and we will address them at the end of the talk. Before we get started, I just want to introduce SZNet and what we're doing this morning. So SZNet is an international network of networks. Is an international network of networks that has a goal of building an international community studying subduction zone geohazards. We currently have 14 different networks, which you can see on the map at the bottom right. And we are always looking to grow. So the idea behind these workshops is to help build that robust scientific community. SZNet towards this goal has several main missions, which you can see on the screen here, which all involve comparing observations of subduction zones, cooperating to consistently instrument critical subduction zones, as well as to develop and nurture early career scientists who can then take up the mantle towards these goals. As part of this diverse and robust community, we value your feedback. So we would love if you are able to give us your suggestions for workshop topics and speakers. You can do that by clicking this link on the left. And then also what really helps us towards improving these events is hearing from you. So please feel free to fill out the anonymous demographic survey. That is that link on the right. So without any further ado, I would like to present our speaker this morning, Dr. Onno Oncken. Dr. Oncken was formerly a professor of tectonics and sedimentary basins at the Free University of Berlin, as well as the director of lithosphere dynamics section at GFZ Potsdam. Dr. Oncken's research focuses on plate boundaries, mountain building, and earthquake cycle deformation. He has been involved in designing and running many international projects to study subduction zones, specifically in South America, as part of IPOC and TIPTEC. Dr. Oncken has also been actively supporting various European projects to promote junior scientists, including the European Marie Curie Initial Training Network, Zooming in Between Plates, and Subduction project, which focuses on understanding subduction. We are thrilled to have him give this keynote presentation as part of this workshop, so please join me in welcoming Dr. Oncken to this virtual stage. And without further ado, I will pass along the mic. Thank you and welcome.
Thank you, and let me hope that it works now. So you see my screen?
Perfect, yes.
Perfect. Thanks again for having me in this great workshop. Fantastic topics, some of them that have been fascinating me for decades. And I'd like to talk about an issue, exactly one of these issues that I've been involved in personally for a while. And that is still one of the active fields of current research that I'm pursuing with a lot of colleagues of mine and students. So you all know this classical image by Shreve and Clues that really made us aware that the subduction plate interface is not just a line as you find it in textbooks, in old style textbooks, I should say, but that it's really a complicated zone that is best and most easily defined as a kind of velocity gradient zone, as shown here on the right, if you take the simple-most explanation or definition of what a subduction channel is. In more recent years, this was updated by an important review paper by Chris Rowe and her co-authors, summarizing of what we knew about subduction channels, and showing that it's not just a simple velocity gradient zone, but that it's composed of a diversity of features such as discrete faults, mélange, block in matrix structures, and so forth. And obviously it hosts a very substantial number of the global earthquake activity of our planet. Now, one of the aspects of this compilation becomes evident as you show that this compilation is based on a huge number of observations from a range of places on this planet that reflect quite a diversity of plate tectonic settings. And what I would like to do today is take you to a simple field tour plus some geophysical observations in an area where we can do it all in a single place. And this is the European Alps, which by chance have a complete preserved subduction channel from the very shallow temperature regime of around about 100 degrees C. And you can walk down this line crossing the isotherms, the metamorphic isogrades, down to a depth that is approximately the depth that we infer to be the down dip end of seismic locking. And you can even walk further west and look at this plate interface deeper down to about 550 degrees C. In all these cases, the subduction channel is there, or what we consider to be the subduction channel, and the base of the upper plate, which is shown here in light brown, the Adriatic upper plate, or part of the African craton that, as shown here on the right side, forms the upper plate. So with the Piedmont Liguria Ocean closed before initial collision with parts of Europe, which we call the Briançonnais, has happened, that is terminating the story. So we have indeed this record at hand, and we can do this little virtual field tour by showing you what we are able to find. And one of the justifications why it makes sense to use this as a key setting is that we know that the interior plate interface zone froze at nearly the same moment in time, around 45 million years ago, with the onset of underplating of the European continent that was subducting beneath Africa. But also, if we look on the right side here, and you see that the metamorphic conditions are very much alike those from a range of convergent plate boundaries around the planet, whether we are looking at very fast subducting systems like in Japan, or slow subducting ones like in Cascadia. So the alpine system is a very good representative of a range of convergent plate boundaries. Having said that, let's go into the field, and this is what it looks like. Nearly perfect exposure, as you see. And this nice setting is a view of the complete subduction channel from the left, which is the underplated part of Europe. The top here is the Adriatic plate, or part of Africa, and anything in between is the subduction channel. And mapping it a bit in detail, this is what it looks like. It's round about 1 kilometer thick. It's composed of a complex melange of pieces from the oceanic lithosphere, like this little hill here, which is a bunch of pillow basalt lava that was extruding at the seafloor in Jurassic times. Or you also have pieces like here of continental crust and sediments involved. So it's important to note that we have both material from the lower plate as well as material from the upper plate, and obviously the trench sediments involved in building this melange. And the simple reason being that this is one of the margins that has been dominated by subduction erosion before it moved into the underplating and accretionary mass flux moment. So it represents, again, a margin, as we know that the majority of margins globally is in subduction erosion mode. It's representing what we see globally in most cases. Another aspect that I would like to point out right now, I will always show you the temperature where we are, so you can see and compare the observations at different temperature and depth levels with each other, pointing out what changes with depth and what not. Okay, let's look at other places where we have the plate interface zone exposed, like here at 380 degrees south. It looks very different from what I've shown you before. The one at 280 degrees again shows this predominant melange type units with large blocks comprising both upper plate and lower plate material in the melange. But here what you see is a block-dominated subduction channel system with very large blocks and very little matrix, so to say. And we have this variability all along strike. So it's one of the characteristics of this plate boundary zone that there's not a one-of-a-kind block melange or block matrix ratio. It varies enormously along strike and down dip. And this is probably an important aspect that one needs to consider if one wants to understand the diversity of subduction channels globally. Moving on, let's take a look at the top of this subduction channel. In all these cases, it's a knife-sharp boundary. You can virtually lick it. It's at any temperature range that you look at, it's very sharp and comprises the melange type or master fault rocks immediately below it. And as you see here, for example, on the right side up here, typically the master fault that accumulated most of the displacement has a thickness of about 10 to 20 meters. That's something that we find in the entire system at whatever depth range we're looking at. But again, the master fault also varies in terms of its composition, and we'll have a look at that by now looking in more detail in this master fault here to get an impression of what the rock fabric is telling us. So if we zoom in, it's ultra-cataclysite, blackish, extremely fine-grained. It has a distinct wavy foliation that you see, and it is cross-cut by principal slip zones, these PSC nominated thin shear bands that are extremely sharp and have a width of a few millimeters to maybe a centimeter, cutting the system not just in the master fault, but also as you go down directly beneath it, a few meters below, where we are already in the fleche domain. You see these very sharp principal slip surfaces coated with blackish, ultra fine-grained ultra-cataclysites. And another feature that you immediately see that this unit is also cross-cut by numerous veins that have been completely fragmented. So there's a lot of hydrofracturing. Most of these veins are quartz, but we also have, depending on host rock, variations in the lithological component or mineralogical component of these veins. You have some of them that are completely fragmented and dissected, and you have other that are more homogeneous. You see still some linear features here that are just beginning to become disrupted. So there's multiple generations of hydrofracturing taking place in this master fault unit. So if we look at these cataclysites, this is the one type of cataclysite we find. And again, you note with interest that it's found at all depth ranges or all temperature ranges. And these are clast-rich cataclysites. So you see the individual clasts that are beginning to fragment and fall apart at all scales. And typically this is independent of rock type. All rock types produce these clast-rich cataclysites, where the clasts are floating in a matrix that has a sometimes stronger, sometimes lesser expressed wavy kind of foliation. But that's only one type of a cataclysate. We have a second type, and that's this one. And again, we have these principal slip zones that are very thin, just a millimeter or a few millimeters to a centimeter thick, filled with class poor, a blackish ultracataclysite that is extremely fine-grained. Indeed, in some cases, this ultracataclysite even acts with injections into the host rock, so it's not only there at the slip plane, it also injects the host rock in some cases. And we find these principal slip zones to very large depth, as you see down here on the right side. Again, independent of rock type, it doesn't care about rocks and rheology, it just happens in all these depth ranges. And often enough, like here, this is a piece of the master fault at 400 degrees C. You see that the bulk fabric ranges from proto-cataclysite to clast-rich cataclysite. And then we have these thin principal slip zones filled with this blackish stuff. So in summary, there's two types of cataclysites that we're able to find. Some that suggest that it's another mode of motion than the ones that are very thin. Those of you familiar with the drilling experiments that have been done, for example, of Tohoku, drilling the Tohoku master fault, find that indeed it's this principal slip zones that are extremely sharp and covered with this extremely fine-grained ultracataclysites are candidates for seismic rupture, while these clast-rich cataclysites that you also see here are probably not. They are another mode of deformation that I'll look at later. Okay, we also have pseudotachelites, obviously, and we not only have those fairly fresh, as seen here, with nice injection veins into the host rocks, a feature that they share with these very sharply bounded cataclysite zones. They also appear in multiple generations, like seen up here, where we have an older pseudotachelite that is already devitrified and myelinitized, cut by a younger one. And from current work on age dating, we find that we have about 40 million years of earthquake history virtually stored in these pseudotachelites that show a history of 40 million years of earthquakes during the convergence history of this unit. Now, what is another important aspect is that these foliated pseudotachelites sometimes co-occur with these ultracataclysites on principal slip zones, on the thin principal slip zones, telling you that you have both conditions apparently occurring at seismic style deformation. This is not happening with these diffuse clast-rich cataclysites. That's a different story. Another aspect that's immediately evident also from these rocks, the pseudotachelites only appear at the base of the upper plate, in the basement rocks forming the base of the upper plate. They do not appear in the subduction channel because obviously the conditions for rock melting were not appropriate there, but there, that's where we have these thin principal slip zones coated by blackish ultracataclysites. So they're replacing each other, but both very likely reflecting earthquake slip. Now, another pervasive feature that we find in the entire subduction zone is the dominant, the fabric feature dominating everything is pressure solution creep. There's virtually no to very minor myelinitization only, even at very high temperature. Pressure solution is the dominant mechanism that we find at all depth ranges, but obviously increasing in fabric style as we go towards depth. In many cases, it becomes difficult to really realize that the right side here, for example, is a part of the master fault at 400 degrees C, that this was once part of the master fault, but you do find remnants of the clasts as shown here, smaller and bigger ones that are still enveloped there, or rock fragments that are embraced in this melange unit as exotic components that are sourced from different sources. So the feature is still there, and even at this depth, we still find remnants of these principal slip zones, as I showed you before. And obviously, throughout the entire system, we find abundant evidence for hydrofracturing. They can be huge, as the one shown here in this left side picture at 400 degrees C, and smaller like the one here on the right side. Overall, as we measure their properties from near trench to further away from the trench, we note that the number of veins increases drastically towards depth, and so does their length and their width. So the role of hydrofracturing indeed increases with depth. One of the few changes with depth that we're able to see, in contrast to the ones that I've shown you before, that seem to occur at nearly all depth. One aspect about these veins is important to notice. You see already up here, the crystals look rather blocky. There's a number of papers out that suggest that fibrous growth is indicative of creep in the seismogenic zone. What we note with interest is that fibrous growth of these crystals does not occur in or close to the master faults. You do find it in the melange once in a while, but the dominant fabric is like this, and it even goes a step further, like this example shown here, where you have obviously euhedral growth of crystals. And you can only grow crystals with their own crystal faces if you do this in a fluid-filled void that you keep open long enough for the crystal to develop its own crystal faces. And this is a feature we find at all depth ranges that is very indicative of practically lithostatic pore pressures that must be existing long enough to have this kind of growth feature occurring. But again, the same feature is then overprinted by pressure solution creep, as this rock fabric here on the right side shows again. So that is an important aspect to reconsider. And last not least, last outcrop, looking at the base of the upper plate and why there is so little hydrofracturing there. The hydrofracturing that I've been mentioning is indeed focused on the subduction melange, and there is surprisingly little in the base of the forearc upper plate. Here, for example, you see just one vein trying to get into the upper plate. This is the contact zone, but it doesn't make it very far. But whatever you see is this greenish color of the basement rocks that is a diagnostic image of retrograde mineral reactions taking place here, mainly forming chloride and phyllosilicates from the original basement rocks, and the formation of an associated foliation. And what this does is very simple. Virtually all retrograde reactions forming phyllosilicates and chloride are related to positive volumetric dilatancy. Hence, they occupy a larger volume than before the reaction, and that invariably destroys all pore space, and fluids are practically prevented from migrating from the subduction channel into the forearc by closing down any pore space and forming these reactions that you also see nicely in these cracks here on the right side, where you have this greenish color expanding from cracks that the fluids have tried to use as escape routes. So we are forming something like a transient seal at the base of the forearc plate that is only cracked once in a while when an earthquake happens and is able to break the seal. So all of these field-based observation we can summarize in something like a generic fabric image of a subduction channel. And you see this summarized in this view graph with a subduction channel that has a couple of 100 meters to maybe a kilometer thickness, that has a master fault at the top that has a typical thickness of about 10 to 20 meters, varying a little bit. But it's not the only fault. There's a number of additional faults dissecting the subduction channel material itself. And there's a range of fabrics that we can monitor all the way from close to the trench. We don't have the trench exposed, unfortunately, from close to the trench all the way down dip. And there there's a few funny aspects that need to be considered. One is, and I summarized them with what I call the apparent stress fabric paradox. So let's have a look at that. For example, we have solution precipitation creep from very close to the trench all the way down dip, increasing in intensity down dip. But solution precipitation creep wants low strain rates, and it does not like high pore pressure. The next feature is brittle rupture and fracture that may be seismic or aseismic. That does not care much about the fluid pressure, but it wants higher strain rates, in particular as you go deeper to temperatures that usually are considered to be in the ductile regime. You need to have higher strain rates to allow a brittle fracture to occur. The fluid pressure, the sublithostatic fluid pressure that seems to be extremely high in many parts of the system, well, this needs a seal once in a while. Otherwise, how do you keep the fluid down there? Making a seal, however, does not allow high strain rates to occur. Otherwise, you are not able to close down the pore space. And the pseudotechylites that we see at the base of the upper plate, they want low pore pressure and high strength. Otherwise, you do not generate enough shear heating. So you immediately notice that these fabrics that are all mutually cross-cutting each other from cross-cutting relationship require a cyclic change of pore pressure, strength, stress, and strain rate. So this is something that does not come as a huge surprise, because we know that earthquakes and interseismic periods change kinematic conditions at plate interface zones, but they require some deeper thought on how to get to the details of how this has been occurring. Okay, so let's step to what we can say from the geophysical side. Obviously, one of the key tools to do this is from seismic imaging, because it provides a fairly robust geometric image of what the system looks like. But the question marks drawn here in this image immediately pose the question, what is the nature of these reflections? Are these lithological? Are these from transient petrophysical states, for example, fluid-rich layers? Or do they have a kinematic meaning? This is fairly unclear, and one of the big weak issues of reflection seismic imaging. We cannot really identify what exactly the subduction channel is, because we don't have kinematic indicators. We might combine this, as shown here on the lower side, with analysis of the pore pressure ratios from a variety of tools, either from VPVS tomography or from reflection coefficient analysis and so forth, to see whether there is indeed a coupling of the reflections with some change in the petrophysical properties. But which part is forming the velocity gradient zone that I was talking about initially? Same with the work that we did along the Chilean margin with the UNCORP study, doing a reflection seismic image of the system. We find beautiful reflections from the plate interface at depth, like here or higher up. Note this gap. I will come back to this kind of reflection gap later on. Here is where the seismicity happened. This is the seismicity from the Antofagasta earthquake projected into the plate interface zone. And you have a more highly resolved image down here, combined in this case with VPVS tomography from before the earthquake. And you see that the zone of high VPVS anomaly is constrained to the oceanic crust and the subduction channel itself. It does not expand into the upper plate. It changes completely after the earthquake with all these aftershocks happening. You see that there's a cloud of high VPVS ratio now invading the upper plate above the up-dip end of seismicity and the down-dip end of seismicity with elevated VPVS ratio. So this would indicate that indeed we are looking at something that is related to breaking this transient seal that the rock record from the field tour was imaging right before. But the seismicity is an important kinematic indicator, and we might use that to get a better view of what we consider to be the subduction channel. This is seismicity with a reflection seismic image now of the 1960 Chile earthquake area, and you see that at the nucleation site of the 1960 Chile earthquake, we have virtually no relevant reflections. We again have the same kind of reflection gap as I was mentioning before. Nice reflections up dip, where the downgoing plate is in contact with the upper plate continental crust of the forearc, but also where it is in contact with the forearc mantle wedge. We have nice reflections, broader, forming a broader base, but obviously reflecting something that is distinct from the crust. It even becomes more important if we do a more detailed processing. In this case, processing only low frequency P wave, and up here only processing S wave reflections. It turns out that this zone, this nucleation center of an earthquake, is characterized by variable petrophysical conditions that control our reflectivity, but we cannot say exactly what it is. It's just pointing out that there are critical changes of petrophysical parameters. The seismicity, if looked at in detail, also images the subduction channel. This would be the blue band of seismicity that we're seeing here. The green one would be within the oceanic plate going down, and the pink one would be in the upper plate of the northern Chilean forearc. What you see here is that the blue band has a width of several kilometers. That's the best we can do with seismology, at least until recently. Just now, a paper was published where we were looking at an earthquake that occurred in Ecuador. And fortunately, there was a large seismological network out, and the earthquake happened at a fairly shallow depth of about 20 kilometers right below this network. So in this case, in contrast to the Chilean cases, the earthquake was right beneath the network, and hence depth resolution issues are minor as compared. And you can directly see this in the resultant data that is showing the aftershocks. And what you see here is that the aftershocks are not statistically distributed in the system, but they're aligned. They form what the author calls families of earthquakes that are obviously aligning along secondary faults within the system. And doing this through the entire system, you can see that there's round about a kilometer-wide zone of these aftershocks that are, as I said, not statistically distributed, but focused in these earthquake families. And these aftershock families, if analyzed and processed in more detail, turn out to have a characteristic thickness of around 20 meters plus or minus, give a few. And interestingly, this leads us to the conclusion that this would be a real high-resolution seismological image of the subduction channel active during a part of the seismic cycle, namely during the aftershock part. And the kind of generic concept would be something like the one that we drew up here in the lower half, with a master fault at the top of the subduction channel of about 5 to 20 meters width, like most of the other faults, and the entire zone a few hundred meters to maybe a kilometer thick, but forming a plate interface fault network. Very much what we saw in the field, with a number of shear zones delimiting individual units within this subduction channel. I'm pointing this out because one of the conventional debates has been that if you look into a fossil subduction channel as the one in the Alps that I was introducing you to, the expectation is, oh, you're not looking at a system that was active during a single seismic cycle, but one that was again and again overprinted by multiple deformation events for millions of years. And therefore, the image that you get from the mapping and that you get from the drawing of a cross-section is showing you a progressive stacking through time. Our age dating says no. It says the entire system froze at 45 million years ago. And this data that we now have from Ecuador supports that indeed you have this entire system being active as a velocity gradient zone during short time scales that are relevant for instrumental observation. So basically at the seismic cycle time scale. So what do we know about the thermal, kinematic, and mechanical properties? This is nicely summarized in this study by Gao and Wang, showing that for a range of margins globally, from thermal and mechanical modeling, it becomes clear that there is a distinct distribution of those zones that are prone to seismic rupturing and those that are obviously focusing episodic tremor and slip, as well as silent slip events, are closely related to the thermal conditions, but also to specific mechanical conditions that are outlined here by these numbers that you see here. So we were taking a closer look at that, doing a complete analysis using a variety of methods, mostly about heat dissipation and Coulomb wedge analysis, to understand what is the effective strength of these plate interface zones. And you see this in this image here on the right, that indeed the tectonically supported elevation is equivalent to the maximum mean elevation that we are able to measure, telling us that wherever we measure globally, the system is in force balance. But not only that, if we compute the average coefficient of friction based on that, the values that we get are this. So the effective coefficient of friction of a plate interface is about an order of magnitude below Bayerle's law, so indicating that it's much weaker and needs to be sustained by pore pressure. And the pore pressure range that you get from estimating the pore pressure needed to support this very low effective strength is round about 0.87, so very elevated, similar to what the rock record was beginning to tell us. But I was mentioning before that this is based on techniques that are basically biased towards the long term, or to the average of the long-term ratio effect of the effective coefficient of friction. So this number with the approach chosen here would provide something like the long-term mean strength. And the question obviously is, how does this change as you move forward in a seismic cycle approaching the next big one? And we were fortunate to collect such data before the Maule earthquake during our study of the 1960 event just south of that. Here you see on the right side the degree of geodetic locking before the Maule earthquake, and the lines give you the white lines give you the slip of the Maule earthquake itself after it broke these lock patches entirely. And from the seismological data that we collected during this pre-Maule event earthquake, we were able to constrain the Poisson ratio, converting that into the lambda ratio or the pore pressure ratio for this area. And on the central figure here, you can now see in the lines, in the red lines, this is the locking degree. So very high locking of about 0.8 and higher in the lock patches. And the color code here reflects the pore pressure range that we have. And you immediately notice that there is some kind of anti-correlation. And this is even made visible better if you draw a cross-section here along strike. And what you see here is in brown, the locking, in red, the pore pressure range, and you see that they're exactly anti-correlated. Where the pore pressure becomes very high, this would be here, for example, locking gets low. Where pore pressure is low, locking gets high. And remember, this is data collected about 2 years before the earthquake happened. So we are reflecting here something that is towards the terminal stage of a seismic cycle. And in this case, indeed, before the terminal stage of the seismic cycle, we are dealing with very high values, much higher than the ones that we had previously with the long-term averaging approach. So we're indeed seeing some kind of change here. And this kind of change with respect to kinematic cycling at the plate interface has also been observed elsewhere. For example, in this study by Warren Smith on slow slip events along the New Zealand margin. And this was done using changes of the stress tensor that are interpreted to reflect not just a cycling of stress, but also of the hydraulic state during the release of such slow slip events. But to be honest, there's few such observations at this point that tell us how the hydraulic state may be varying with changes in kinematic behavior. And the same goes for the question of, well, if an earthquake breaks, how fast does such a subduction fault recover, and what are, sorry, that was too quick, how fast does it recover and what processes are possibly involved? This is, again, back to the Maui earthquake, and what you see here is the GPS vectors over a period of a year. And you see them here in the inset even better, that after a few months, they are beginning to rotate back. And decomposing the signal and doing some modeling, we find that indeed relocking is a process that happens very quickly. Relocking happens within a year after such a large earthquake broke, and we expect that the time scale of relocking scales with the magnitude of the event to some degree. So for an 8.8 event, less than a year is not much time. And the system is starting to get loaded again. But we know, to be honest, very little about that. And we don't know which parts of the subduction channel that I've shown you previously are the big contributors. Is it the master fault where the principal slip zones are healing? Or is it the subduction channel itself? And in its entirety, we don't know. So one of the big unknowns is this one. We expect standard stress cycling over time to have this kind of pattern in a very simple sketch. And then we expect that the evolution of strength of the rocks follows this kind of sawtooth pattern with some time where healing and recovery takes place until the rock is back to its original strength. But the standard assumption here is that rock strength is kind of constant. How do we know? Could it be like that? That indeed we go through an early stage of compaction and healing during the afterslip periods with progressive pressure solution creep, healing the fault. And at some point, when the transient seals kick in, preventing the fluids from escaping the subduction channel, you are starting to hydraulically load the system. So this is one potential contributor to reducing the effective strength. Additional contributors could be the grain size. I'll come back to that later, or mineral reactions taking place. So from what we sense today, strength is not a constant, but a variable. And we know very little about how this evolves during the seismic cycle timescale in an earthquake. And one of the big challenges is whether we can better constrain the strength and the stress evolution during the seismic cycle of both the plate interface zone or subduction channel, as well as the 4-arc system. Something we would love to know, but how do we get there? With which kind of observables? So similar to what I've been showing you in the field images, we basically could summarize our observation that we have 3 kinds of kinematics behaviors. We have faults that creep constantly, like parts of the San Andreas, but also subduction faults that creep constantly, like the Hellenic margin. We have others like the Chilean one that are locked and repeatedly break the locking. And we have these kinematics, these transient kinematics, whether it's silent slip events, episodic tremor, and so forth, or as shown here on the right side, after slip bursts. So even after slip, if resolved highly enough, is not a constant process decaying according to the Omori law, but it does this in bursts that last a couple of days to a week, and that are vaguely distributed throughout the system, but closely interact with the aftershock seismicity. So we have this complex behavior that reflects now observed instrumentally the same kind of range as we were beginning to infer from the geological field record. Okay, so summarizing this, we can also now draw something like the generic instrumental signature of a plate interface zone. And starting out with the seismology and geodesy data, it would appear that the locked zone has a 1 to 5 kilometer wide band of seismicity that illuminates the subduction channel. But as I've shown you before, we lack in most cases the depth resolution to really show that in truth, using optimal conditions, this is much narrower, as shown down here, a couple of 100 meters to maybe kilometer wide network of faults that is responsible for accumulating the seismicity. And we have seen that there is a transient stress tensor changes related to episodic tremor and slip, illuminating pore pressure fluctuations. So seismic imaging shows us that in the locked zone, we have one or several sharp reflections. They often tend to weaken up dip. In the earthquake nucleation area, we only have low frequency and S-wave reflections at megathrust nucleation sites, not very well understanding what this is telling us. And below that, we have broad aseismic reflection bands that are variably oriented, but the band overall is parallel to the interface. And from tomography, we see that in the upper plate, we may have transient post-seismic high VPVS in the upper plate basement, but it's transient during the interseismic stages. It's confined to the plate interface zone itself and maybe to the accretionary wedge part in front of it. So this, in a way, summarizes what we know from instrumental observation, and we can add to this what we know from geodetic observation, showing us that we also have this range of kinematic variable behavior from stable sliding, as down here, to the variety or to the family of slow slip features, all the way to the asperities locked during the interseismic period and responsible for the large earthquakes. Now, having looked at that, the interesting question is, can we get a better grip of these different kinematic regimes that we're able to identify within the subduction channel? And this is best done by going back to the instrumental observations. So we know that earthquakes have slip velocities in the range of around about 1 meter per second, constant creep on a plate boundary. So those that are not locked, that are constantly creeping, like the Hellenic margin I mentioned before, they would need a creep velocity of about 1 to 10 centimeters per year. That's the order of magnitude of plate motions that we are able to measure. And we would need to know over which width this is distributed better. For the diversity of silent slip events, Matt Ikari has compiled this plot showing the range of slip velocities that are somewhere in between. So the interesting challenge, if you want to get a better comparison towards a geological field observation, is that you need to convert these velocity observations to a measure that you can relate to rock fabrics, and that requires us to convert this into strain rates. So if you do that, the simple-most approach to do is just to take the fault score displacement scaling relationship that is well known since decades, since Chris Schultz started this work in the 80s. And we have a fairly straightforward scaling relationship that relates the thickness of the fault core, as shown here on the right side, to the displacement. And using the displacements which are measured, we can estimate what the fault core thickness of these events must have been at depth. Based on this observation here. And the uncertainty is round about an order of magnitude, just to give you an idea, which is acceptable given the other uncertainties that we're dealing with. And then we get something like this. So you again, interestingly, see these three different styles of kinematic behavior that also the earthquake, also the rock records and the instrumental record were pointing at. We have a family of earthquakes, all the way from low frequency to standard earthquakes. We have this family of slow slip features that embrace a fairly narrow range of shear strain rates. And then we have the steady state plate convergent rate for those margins that are constantly creeping without being locked and without having earthquakes. So that's the strain rate needed there. So here we are, and the question, the first question that obviously comes into mind is this telling us anything about whether the gaps in between might be filled with observables? Here, no. Here, maybe. We lack instrumentation that is able to resolve any features that are occurring here, but the current instrumentation we have would detect anything that is happening here. So we next just go to the diverse deformation mechanisms that I've been showing you. So we have dislocation creep, we have solution precipitation creep, and we have cataclastic flow or stress corrosion creep or brittle creep, what you want to know, which is a composite from rotation, rolling, frictional sliding, and microfracturing. For all of these, by now, we know the constitutive laws that describe this from experimental work in the lab. And I'm just highlighting here these equations. Some parts of the equation that I'll come back to later is the fact that these three here are sensitive to the effective normal stress. This one not, but it's susceptible to the peak differential stress at depth, or the difference between strength and the peak stress. So you have diverse relationships expressed here, and I'm using two laws for solution precipitation creep, something you could consider a lower bound, which is a pore-free granite, to an upper bound, which is a highly porous rock. And now projecting this into shear zone space, using the Obara and Kato image, what we find is the following. We have the vertical segmentation of a plate interface zone that we have here from 0 at the trench to about 500 degrees C. And here on the horizontal axis, I plot the shear strain rates that we calculate based on these constitutive laws. And I start doing that for a pore pressure ratio of about 0.7, which would be, let's say, towards the lower end of what is being reported for plate interface zones. And this is what we see. Earthquakes plot at this shear strain rate. This is where we would get flash heating, pseudoteculite formation from rock melting, gel formation, and so forth. This is what we get from dislocation creep of quartz that would form myelonites, or you would consider to be the conventional representation of the brittle ductile boundary towards depth. But you also see that this boundary is strongly sensitive to the effective shear strain rates that you're having. And finally, we have here the solution precipitation creep for very high porosity. We have the solution precipitation creep for very low porosity, the granite. And you see immediately that the grain size plays a huge role, taking these curves apart by several orders of magnitude. So the grain size evolution during the evolution of the subduction channel has a prime control in addition to the temperature in terms of the behavior. And down here, I plot, as mentioned before, if the plates were moving past each other without getting locked, this is the shear strain rate needed. And the variability depends just on the thickness of the fault that is accommodating the slip and the convergence velocity of these two plates. And last but not least, I plot the brittle creep, which turns out to be here. Okay, so now we can ask the question, what happens if we push up the pore pressure ratio to the values that I was inferring to based on instrumental observation, which is close to lithostatic? Again, not just instrumental observation, also from field observation. This is what happens. You see that the thermally activated mechanisms like dislocation creep and solution precipitation creep are moved out of the system because of their sensitivity to the normal stress, while brittle creep doesn't care. What I just add here is this line here. This would be at 75% of or stresses of 75% of the peak strength of the rock. And you see this does change a little bit. This boundary, however, is important because it's this strain rate limiting factor found in experiments. You need a stressing rate that is higher than round about 75%, because the crack growth is the limiting speed limiter for this mechanism. So you need to have high enough stresses to allow brittle creep to become effective. But most interestingly, if you now plot all these slip velocities that have been reported for the family of slow slip events, they beautifully align along this curve of brittle creep, indicating to us that very likely this is the mechanism that is most likely responsible. Even if you would allow slightly lower pore pressures to exist, there's no way that you can get the solution precipitation mechanism into the proximity towards the instrumentally observed slip rates. So very likely, indeed, it's cataclastic flow in these clast-rich massive cataclasites that I showed you from the field record that play an important role in doing this. Now you can take this a step further and look at this through this flying carpet that again here shows the temperature evolution from 50 to 500 degrees C, and here now for a complete loading cycle. So normalizing the stress such that you're normalizing it to the strength of the rock. So at the value of 1 here on the left side, this would mean that you're reaching the strength limit of the rock and would get unstable rupture with an earthquake. And here on the vertical axis, I plot the shear strain rate. And this flying carpet is now the composite of all the strain rate mechanism or mechanisms contributing to strain rate in the subduction channel system. And you find that at the conditions that I show here for a lambda of 0.8, this part of the system should be locked. Here you should have solution precipitation creep doing a good job. And towards the terminal stage of the seismic cycle, brittle creep is more likely to jump in and control the deformation mechanism. If you do the same gain for near lithostatic pore pressure, you see what happens in the early stage of the seismic cycle. Locking is better expressed. For the final stage, there's no difference. At any rate, you are controlling the way that you have different kinematic responses in the subduction channel during different stages of the loading cycle, just using this experimental approach. You can also take this a step further. Now I just focus on 200 and 400 degrees C. 200 would be right in the middle of the seismically locked zone. 400 degrees should be right below the locked zone, to see what happens if we do this and explore the flying carpets, what they're telling us. And now I open this axis as the pore pressure ratio. And what we find is that the convergence creep rate required of 10 to the power of 10 per second requires that this system be locked most of the time. Only during the terminal stage should the brittle creep kick in. As you go towards depth, solution precipitation creep becomes efficient enough and may overcome locking at some point. As you go deeper towards higher temperatures, obviously this becomes even more important. And if you now consider a complete seismic cycle in the center, you would have this kind of stress and strain rate evolution predicted by this mode. In this case, obviously, under stable conditions with velocity strengthening behavior, it should rather result in a kind of slow slip cycle evolution behavior. So taking all this together, we can now summarize a conceptual fault model for a subduction channel, starting out with a classical textbook example by Simpson, who has drawn this for intracontinental faults or the continental crust. We just update this now with the observations that we have from the subduction channel, and this is what it would look like. We have a through-going system with a fault network that does much of the action. We have pseudotechelites, however, only in basement rocks, mainly in the base of at the base of the forearc. We have hydrofracturing throughout the entire system. We have here a zone that is interesting because it looks like there is a gap in behavior. That's why the lines are dashed. This is something I haven't mentioned, but this is something that has been found globally along convergent margins in the work of Gao and Wang that I was just mentioning. It's pointing out that deep episodic tremor and slip seems to be separated from the seismogenic zone by a gap zone that is kinematically different. But what we do see in this zone is also foliated cataclasites and hydrofracturing. So the difference is not fundamental. And here on the right side, we see how the stress conditions and the hydraulic conditions may be considered to be operating. But again, I note we don't know the temporal evolution, and the spatial resolution from instrumental data is very limited. And with this, I would like to come to my conclusions. What I can see here is that from the diversity of observations, both from instrumental imaging as well as from the rock observation in exposed and exhumed subduction channel, we are dealing with 100-meter to kilometer thick network of faults that embrace units with very variable Mélange and block ratio. Interestingly, the scaling of this width to displacement is quite similar to conventional scaling laws found to be relevant for fault damage zones. We see that the subduction channel operates at the seismic time scale, the seismic cycle time scale. Does it also do so shorter? For the aftershocks, it's obvious, but we don't know how it kinematically operates in the middle interseismic or the late interseismic timescale. We lack such data, so a big challenge for the next generation. We see that the subduction channel velocity gradient zone is dominated by three kinematic regime features, from earthquake slip, slow slip, family, and continuous creep. These are found both instrumentally and in the rock record along the entire length down to more than 500 degrees C. So that is not in agreement really with a simple brittle ductile assumption, ductile boundary to be of relevance for a subduction channel, likely because the hydraulic conditions and the strain rate conditions are much too variable to allow a simple brittle ductile boundary to be in place. We have an apparent stress fabric paradox from the competition of solution precipitation creep and brittle creep earthquakes that is indicative of cyclic pore pressure, of cyclic stress, and of cyclic healing evolution. But we also have a transient seal at the base of the upper plate. In all these cases, the time constants, the spatial and temporal scaling, and the evolution of key properties are unclear. Another huge challenge. We can infer this from observations to play a role, but the quantities are not clear. And this has consequences because most of the models that we have for subduction channel, be they conceptual or numerical, they're incomplete. They're focusing and doing this very successfully for individual kinematic or physical properties of the subduction channel and its image that is mostly static, but we don't know what controls, for example, lock patches. It's a matter of debate to this day. We don't know what controls earthquake nucleation sites. We think a lot about what kind of feedbacks may be existing. Overall, a complete model of the subduction channel and its surroundings would have to be able to explain these features and provide a coherent, complete image of the system. So a big challenge for the next future. Thanks for your attention.
Thank you so much, Onno, for a very inspiring talk, as always. And it covered both short-term observations or instrumental recall and also long-term observation. Thank you so much. So now the floor is open for questions. Feel free to put your question either in the question and answer window or in the chat, please. We already have a couple of questions. Maybe I can start with the first one. Yihe Wang is asking, thank you for the fantastic talk, Onno. The geological structure of subduction zone channels you showed earlier suggests a mixture of mineral types and large variation of material properties, for example, elastic model in the channels. Do you think the earthquake cycles and the plate interface kinematics are so governed by the variation of such a material properties besides the stress and pore pressure changes?
To be honest, I would not be surprised. We see, or we generally assume that lithological change from mineral reaction and grain size, for example, are slow processes. So at the short time end of a single seismic cycle, I would be careful to predict that it plays a huge role. From experimental work, however, we know that as soon as fluids are present, and we see that these are present the entire time, rates can accelerate dramatically. So whether be they mineral growth rates or reaction rates, and this invariably has a consequence for the mechanical properties. This is inescapable. What this may do, maybe an idea for a few clever experiments, but I know that experimental rheologists hate doing experiments at elevated pore pressures because they pose a security risk for the experimentalists. So getting there and establishing the mechanical influence that these processes may have on the mechanical properties is a big issue for the future.
Great, thanks, Onno. Let's move to the second question. Is Baoning Wu is asking, thank you for the great talk, Onno. It's very insightful. In a slide, you show the brittle creep mechanism that explains this aseismic transient strain rate, which you said is about 1e minus 4. I wonder why aseismic transient strain rate is almost 1e power of minus 4, 1 per second. Assuming a 100 fault width, would this value means 1e power of minus 2 millimeter per second slip rates? This value seems higher than what is observed, or maybe I misunderstood your graph.
I should have clarified this. What I show in the graph, and you also see it still down here on the right side, is the upper bound of the shear strain rates that you can convert from the instrumentally observed data, assuming the scaling ratio between fault core thickness and displacements. Now, this scaling relationship is based on the simplifying assumption that you're dealing with a single event. But as we have seen, we do not only have a single event, a fault core grows over time along the scaling law as it accumulates more and more displacement, or more and more events, as you might say. So I'm not showing this here on this plot, but if you do the simple math, but by assuming that this transient creep event occurs on the mature, evolved fault system that has grown in thickness, then you get a slower shear strain rate by about 2 orders of magnitude. But you don't get beyond 3 orders of magnitude. So in this plot here on the right side, you would draw the band maybe to E-6, but not further to the right, because that would be larger than the fault thickness that we are able to observe in the field and in the geophysical data would be able to support.
Great. Thanks. So I move to the next one. Hope Wang is satisfied now. So we go to the Bin Hao Wang is asking, thank you so much for impressive talk. Pressure solution is seen at all depths, but the strain rate is very low. Could you comment on more on the role of pressure solution? Does it play an important role in healing?
I would fully agree. I would even think it may be the most important mechanism apart from compaction. Compaction is the standard process found in experimental rheology to be responsible for healing and creating just more grain-grain contacts where you have electromagnetic forces contributing to the cohesion and re-strengthening of the material. But in an active system like a subduction channel, we see that pressure solution, once the pore pressure has dropped significantly, and you see this on the plot here down in the right, for low pore pressure, solution precipitation creep in fine-grained stuff can become very efficient. It can virtually accommodate the plate convergence velocity entirely in the fine-grained rocks. But the fine-grained rocks during pressure solution creep destroy the permeability. So they create another kind of transient sealing of the hydraulic system, and the buildup of pore pressure will immediately slow down the high strain rates by solution precipitation creep, because you're reducing the effective normal stress. So it's a process with a negative feedback.
Mm-hmm. Very interesting. So Kelling Wang also has a question. Thanks for the great talk. Would the thickness of the channel be affected by tectonic modification before and during examination? Do you see any systematic variation in thickness with depth?
Yeah, that was one of the big concerns we met when we were discussing this with alpine field geologists, arguing that this was strongly affected. In those areas where you have a massive extensional overprint, and this during the exhumation and underplating process indeed happens, there you reduce the effective thickness in some places substantially. I've seen places where it's reduced to meters. But that's very likely not the original one. And you can see in the field observations the overprinting relationships that are occurring at lower temperatures and lower pressures. So they produce diagnostically different fabrics that you can correct for in these reconstructions. For the variability where this is not playing a role, we still see that the variability of the thickness can easily be an order of magnitude. So we have places where it's just 100 meters or so, and others where it's well above a kilometer.
Perfect. Thank you so much. Since we already exceed 1 hour, again, thank you so much, Onno, for accepting our invitation and very nice talk. I don't know if Julie is going to say something.
Yes.
Go ahead, please.
Yeah, thank you, Onno, for this great talk. Thank you, everyone, for attending. We really appreciate you taking the time out of your day. I just want to say very quickly that our last keynote talk will be with Dr. Keelan Wang. It'll be this afternoon at 4 p.m. PT or 11 p.m. UTC. That will also be recorded. And then tomorrow we are starting with our breakout sessions. We very much recommend attending at least one to help foster this robust scientific community and help with the conversation surrounding these topics. So we hope to see you all there. And thank you again, and have a great rest of your day.
No, thank you, everybody. Thank you, No.
Thank you.
Thank you.